Okay, so welcome to the second week of this GIAN course on evolution of wireless systems toward 5G. So I think what we agreed last time was to basically give a bit of time to finalize the discussion on the second paper, which is about new waveforms. Now, I'm not too sure how many of the paper club team leaders are here. I think I see only one, if I'm not wrong, right? Yourself. Anyway, so we can maybe give you 5 to 10 minutes to wrap up this discussion. Now, before we do that, today is a bit of a special day, so we have some different program going on. So there are actually 3 things that are different compared to the usual schedule. So I will have my 2 lectures, and that's okay. Now, in between the 2 lectures in the morning, from 10:15 to 11:15, we have Professor Sanjay Kumar from IIT Mesra in Ranchi. He's a very good friend of mine. We have known each other for some time now, probably 10 years or so, yeah, a bit more. So I'm very pleased to have him here, and unfortunately Professor Suvra can't be here because he has an external examination duty for some master thesis in another city, so he will be back tomorrow, but so today it's us, and I request also you address Sashank Tiwari, who is a PhD scholar here in IIT KGP. So if you have any questions, kind of the deputy of Professor Suvra as course coordinator today. Yeah, so that's something to keep in mind. Now, the first session, Professor Kumar asked me not to tell what it is about, so it's a surprise. I would suggest you attend it. It's special. It's not necessarily of a technical nature, but it's going to talk about techniques nonetheless of a different kind. So it's a very nice complement to the technical program of this course. So that's one thing. So we'll have a small break after the first lecture and before the second lecture, and this hour in between, where Professor Kumar is going to bless us with his knowledge in this alternative domain. Good. Okay, then we have the lunch break, and then I think you have a demo session, right? Is it 3 to 4? All right, yeah. And then there is again a small break, and then we have the last lecture of the day from 4:15 to 5:15, given by Professor Sanjay Kumar again. This time is on the subject of channel modeling for 5G. Am I right? So it's actually very good, a very good complement to the technical syllabus of this course, because we don't touch that. We don't really touch upon that, just bits and pieces, but we don't do that. So it's actually a good complement, because the channel is the basis of all the communication systems, right, and signals. So it's something we have to be keeping in mind. And this lecture is going to be given in the seminar room. So again, Sashank, is your point of contact in case you have any questions. It's close by. It's basically a corridor that is parallel to this, like one block down, so to speak. Yeah. Okay, so I know it's a lot of changes. So if you have any question, let me know. Okay, in the breaks, but we'll work it out. I'm sure it's going to be an interesting day. I think a bit packed, but going to have a lot of interesting sessions and discussion. Okay, and then tomorrow we are back to the normal schedule. We do have a night together at Vikramshila, again close by, on Wednesday night, right? So it's nice. Last time we did it, food was excellent. Discussions even better. So it's definitely a nice way to wrap up the module. We'll have another tutorial tomorrow. So the afternoon sessions are going to be, again, today I explained. Tomorrow we have a tutorial paper. On Wednesday we have the last tutorial paper, and then we have the exam session and the valedictory session on the last afternoon. Okay, so it's going to be hectic. Also because this week we have one day less, right? We finish on Thursday, so. But again, I'm sure we will enjoy and work it out. Okay, so who is present of the paper club teams, leaders? One. So I would say you have up to 10 minutes to wrap up the thing, so you can come, Yeah, come. Yeah. Don't be afraid of the stage. The audience isn't too big after all. So introduce yourself, and then you You tell us what is your take, okay, on new waveforms and so on. Yeah. Speak.
Good morning. I am Zaki Ahmed. I am from Pune Institute of Computer Technology, Pune. I am just going to give a brief takeaway from the paper given. So, first point I wanted to explain regarding the OFDM. What is OFDM, how it is better than the earlier frequency division multiplexing. So, it is basically an orthogonal set of subcarriers which reduce the usage of bandwidth with almost 50%. Then the implementation of OFDM is very easy after the implementation with IFFT and FFT. That is one of the greatest advantages we got with OFDM. The ace of integration with multi antenna system is very easy with OFDM. It has some limitations, like due to cyclic prefix the bandwidth is restricted to 7% and accumulated it is almost taking 16% of bandwidth. Due to the large lobes, it is creating interference. It has a high peak to average power ratio which reduces the power efficiency, and it is difficult to synchronize for a large number of users. When we want to implement OFDM system, it gives very difficulty for synchronization. There are some alternatives to OFDM like FBMC, SCM. So, with these alternatives, these drawbacks which just I listed with OFDM can be minimized or removed. Then the paper has given some requirement to 5G, like the data rates, integration with antenna and others, but the thing is they have not stick to one of the technology like multi-carrier or FBMC. There are some conditions given, and depending upon those conditions any one of the technique can be selected. Like multi-carrier, it is good for getting the higher data rates for energy efficiency as they were listed. Then single carrier is good for small cell, then millimeter wave implementation and low latency. For IoT implementation they listed FBMC is better. So, the overall conclusion they have given for virtualization of the air interface and implementation of cloud radio access, network towards adoption for tunable adaptive modulation, they said for different conditions if they choose different techniques. For some situation, like if FBMC is better, so go for FBMC. For some situation, if multi-carrier is better, go for multi-carrier, and for some situation if you need the third one, so choose like that. So, that means you need one adaptive modulation where depending upon the situation you should be able to pick the right technique. That is what our picks. Okay, thank you.
Thank you very much. So, one small clarification I would like to hear from you.
Yes, sir.
See, you made one statement, due to cyclic prefix in OFDM, bandwidth is limited to 7%. What is really the meaning of this term? I couldn't really understand.
Sir, when we have a signal in OFDM, so it requires cyclic prefix which is additional to the information. So, like for sending our information we need certain bandwidth, but for the quality of signal, for improving the quality of signal, we are adding its replica again, which is actually not the part of information to be sent, it is just for some other purpose. So, that information is additional and hence it is extending the bandwidth.
Okay, this is right. So, basically you want to say that 7% extra bandwidth is required
Yes.
You want to say something? Fine.
Not me, sir. Actually, it was the point
No,
pickup.
I understand,
Yes,
but
yes.
this is the statement basically you wanted to make.
Yes.
That we need 7% extra bandwidth.
Extra bandwidth.
We want to use OFDM because it requires cyclic prefix.
Yes, yes.
Good.
Okay, okay. Thank you, sir.
Any other question or comment on the paper? Not. Thank you very much. We are going to start with the new lecture. Okay, so today we start the third module of the course, which will keep us busy for the next couple of days. And it's basically about, so far we saw the first module was about the introductory part, right? So it would be about the scenarios, requirements, technologies, rationale behind 5G, and we also did a bit of history, right? Discussion about the first generations from first to fourth. And then the second module was about physical layer techniques, okay? Massive MIMO, full duplex, millimeter wave, waveforms, okay? So digital signal processing and also some aspects related to frontal and backhaul, right? And possibly moving functionalities into the cloud. So that's what we are going back to the cloud story a bit in this module also. That's what we did in module 2. Now module 3 is about system level. So system level we mean essentially looking at multiple links in a network. So a multiplicity of transmitters and receiver, not necessarily one and one. And we are going to see how topology aspects play a role. Topology we mean how you deploy essentially the not the user equipment as much as the base station. So it's more how you actually deploy the base stations in your network, how you can study that. And then we have some considerations about radio resource management, and an important part of the 5G story, as it was already in 4G, is about sharing. Now the sharing that happened in 4G was more of a spectrum nature. So all the work in cognitive radio dynamic spectrum access was along those lines. 5G has extended this sharing paradigm to many other resources, so we are going back to that. Yeah, and there is a bit of topology considerations, quite a bit also in module 4, when we are going to see how we can use stochastic geometry as a tool to model, deployments. Okay, we're going back to that. So, first lecture of today is about heterogeneous networks and small cell networks. So first we have to understand the terminology. So by heterogeneous networks, we actually mean networks that combine different layers of deployment. So you have macro cells, like the normal macro base stations, and then on top of that network you deploy another set of smaller range or lower power base stations, and this is what we call small cells. They are of different nature. So you might have microcells, picocells, femtocells. There are different variants depending on the power and the capability of the base station. And yeah, so that's kind of the terminology. So why do we care about that? Essentially, there are three ways you can improve the capacity, say the wireless data rate in a system. One is the spectrum. You acquire a larger bandwidth, which means your if you think about the Shannon capacity formula, this is a factor that will multiply the logarithm, so it gives a linear increase with the bandwidth up to some point, because we know that if you increase the bandwidth too much, you're going to saturate because of the noise power, right? So it's not a monotonic increase. Well, it's monotonic, but it's not linear, right? So at some point it would saturate. That's one thing. And all the stories about spectrum sharing, dynamic spectrum access, cognitive radio, these license shared access we saw in this course are in this domain. The second one is the traditional work on phi to increase the number of bits you can actually squeeze in a certain unit of spectrum, and possibly now with these topology considerations in a certain unit of area. So it's the bits per second per hertz, possibly per square meter. But traditionally, radio link efficiency doesn't play with area. It's really just about the number of bits you can squeeze per unit of spectrum, so bits per second per hertz. And things like MIMO, modulation, coding, full duplex. All of these things are actually in this domain. Now, topology is about essentially where you deploy the access points or base stations. And historically, the density has not been too large, so you would have probably something like, okay, you would have Wi-Fi indoor, but essentially for cellular networks outdoor, you would have a base station every few kilometers, more or less. Okay. The picture is changing because of capacity and coverage requirements, so they are actually deploying more and more nodes per unit of area, and that's if you manage interference and other problems like the deployment of, for example, fiber to connect the access points to the rest of the network. So assuming you manage that, that's the best thing you can do, because nothing can defeat a better physics of propagation. So if you get transmitter and receiver closer together, that's the best thing you can do. And that's the reason why topology is becoming has actually been a dominant topic of research in both 4G and 5G for the past 10 years. Definitely, it's been first probably good papers about small cells deployments would date around the end of the last decade. Now we are at the end of this decade, so it's about 10 years of very intensive research on this topic. I think I showed you this plot from Martin Cooper where he showed the factors that led to the increase in wireless data rate throughout time, and the dominant part comes from topology, in fact, from making the range of cells smaller. Okay, so there is a big motivation to look into topology. So just to visualize the difference between the traditional way to do cellular networking and the heterogeneous one, you see that it's basically in the traditional one, which we call homogeneous, you have essentially only one kind of base station, which is the macro base station. And in the heterogeneous one, you have at least two layers of base stations. One is the macro, one is the small cell. Okay, and normally the deployment of macro is a bit more regular because it's something you design from the beginning. Okay, when you deploy your network, you decide over which rooftops, for example, you want to have your mast, right, and your base station. Small cells do not necessarily have to do that. They could be fixed, but they could also be mobile in the sense, not mobile in the sense they move around, not really, but in the sense they could be deployed flexibly. Okay, you could bring your picocell, your micro, especially picocell, you could bring it around as per the need. So if you have a concert or a rally, political rally, you have some event, you could go there with your van and bring the pico. Okay, that's what operators do actually. So you also have the story which is not shown here of the what they in 4G they used to call home base stations. So femtocell. So these are things that the user could deploy indoor, like you do with Wi-Fi. So again, the deployment is very irregular, right? Because nobody is going to ask you to deploy your access point in your room in a specific position. You do what you want, right? So, and it could be that you have neighboring apartments and both users deploy it on the same wall, just on different sides, and that would increase a lot the interference, right? So there has been associated with this kind of randomness of the deployment, two things have happened in the research community. One thing is the emphasis on self-organizing techniques rather than centralized optimization, because you have to have very flexible decision making if you are given this kind of almost random deployment situations. Okay, so it's both difficult and possibly, I think it's difficult, but maybe even impossible to do a centralized optimization in this case because of the numbers, because of the fact that you don't really know where the things are deployed. You can't control it. So the optimization was pretty much the king in the times of homogeneous networking, but it starts to be less and less relevant for this kind of heterogeneous network. So the wilder the deployment becomes, the more you have to rely on distributed techniques. For example, there was a big amount of work done on game theory because of this reason, okay, and self-organizing networks and so on. The second thing that has happened in the research community is because of this, you see, traditionally the random part in deployment is just the users. You have some models to model the mobility of users, the fact that users are not necessarily in one physical position for too long, right? So you do have mobility models like Brownian models, or you do have agent-based modeling, or you do have other things, Monte Carlo simulations, right, with where you actually take snapshots of the positioning. So we have been doing quite a bit of that, but on the base station side, it was always kind of a static situation. Okay, you decide the deployment, you might optimize the deployment beforehand, but then once you roll out the network, that's it. Okay, but you would never do anything, you know, like it would not imply like big changes in the position of the base stations or new base stations coming up. It's not really the case normally. Okay, but in this situation where you have users, possibly operators, changing the position of the base stations almost continuously, then other tools have emerged which are useful, and the most notable one in the past again 5 to 10 years is stochastic geometry. So it's basically introducing some randomness along with the topology consideration. So now the random process is not just the user position, it's also the base station position. Okay. In fact, most of the work in stochastic geometry has been done on the base station side. Now they're starting to apply it also to the user side. But I would say the dominant part of the work has been done on the base station side because of these reasons. We're going back to this. We have a couple of sessions on stochastic geometry and its application to 5G. Any question? So now okay, we can do it. Now the next question is it necessarily worth it? So if we add more nodes, are we guaranteed we get a higher throughput? So why would we do it in the first place? Well, we might have some areas where the macro network cannot cover properly the users, possibly because it's shielded by some abstraction, or it's just, you know, maybe the situation there is not suitable in terms of propagation, possibly because there are really too many customers and you can't really cope, okay, with that traffic. So there are a few reasons you can think of why coverage might be an issue, and throughput is clearly to do with the increased number of devices and the increased capabilities of the devices. So you do have people doing all sorts of things with mobile phones now, and it's not uncommon now that people own more than one wireless device, right? Probably 3 to 4 is kind of an average number nowadays. So these two problems are there. Now, are we guaranteed that adding more base stations to the mix, we are going to get a better network in the end? What do you think? Anybody? Is that always good? And if not, what could go wrong? Interference is definitely a problem, right? Because you have to cope with that. I mean, the nature of wireless transmission is essentially broadcast, right? I cannot pick to whom I'm sending. Well, you can do things like beamforming, but let's say generally speaking, you have to put effort, right? If you just transmit in a plain way, everybody's going to get it. Your receiver, but also the receivers of somebody else, right? And the same goes with you. Somebody might interfere with you. So we are not guaranteed that unless we do something smart, this will work out, right? What could be the smart thing? Possibly power management, you know, frequency resource management, beamforming. So we do have to, maybe interference cancellation. We have to do something, right? It's not just enough that I blanket my network with base stations and that's it. So the work we did we did a bit of work on resource management. As I told you before, my group at the moment is more working towards studying the performance limits. So to see where the game kind of breaks down, and then basically we will have this is kind of an input to the people that design the MAC protocols in a sense, okay, and the resource allocation algorithms. That's mostly what we do. So probably the first you know, paper on heterogeneous networks, or let's say the most influential one among the early ones, is this paper from Chandra, Sekhar and Andrews. It's a very nicely written paper. It's from 2009. Okay, so they talk about spectrum allocation in heterogeneous networks essentially. So, and they actually show that the throughput is upper bounded if you increase the density under some conditions. So actually the area spectral efficiency is going to be bounded because of the intercell interference, in fact. Okay. So here they use a random access to the channels. Of course, you could do better than that, but again, the more base stations you add to the mix, the more difficult it becomes to do optimization. Okay, it's a lot of things to process, and time starts to play a big role. If you have to collect all of this information and take a decision over hundreds of nodes, and each of them have few actions available, the search space becomes really, really large. These are most likely NP-hard problems, which will take a lot to solve, and brute force is out of the question. You might have to do smart optimization or maybe give up optimization altogether. So a big part of the story behind these distributed techniques, like game theory, is around these lines. Okay. Yep. Okay, so I'm going to tell about some possible problems in heterogeneous networks now. This is some work we did in my group a few years back, when essentially 4G was winding down and 5G was, dawning, so to speak. So it was a kind of the transition phase of the two generations. So what happens if all the nodes share the same band? Okay, they all are working based on RDMA, so clearly this is a 4G picture for the moment. We do possibly massively deploy low power nodes, and of course we have to take care of interference. So there are two kinds of interference. You might have macro to low power node, that's what LPN stands for, low power node. So you might have this kind of interference, or you might have the other interference, where the low power node interferes to the macro users. Okay. Okay, so essentially this intercell interference is the problem we are trying to tackle here. It will lead to performance degradation, right, both in terms of cell edge and an actual total throughput of the network. And because of what I said before, like, the randomness kind of the deployment and the numbers involved and the time needed, you have to be very fast in taking a decision, right, because you have to act in the order of a millisecond. So possibly optimization is out of the question. So you might need self-organization techniques. Essentially what we mean is simple techniques that work based on observing the surrounding environment and taking some actions. But you don't have really much communication going on between the different decision makers, and definitely you do not have a central entity deciding for everybody. That's, in a nutshell, what self-organization is about. So we are actually we want to be, conservative about intercell signaling overhead. We do not want to spend all of our bandwidth and time to coordinate without being able to communicate, right? So most likely you will need something more of a heuristic nature. So it's not a real optimization problem. It's more, trying to get decently close enough to the optimum with some things like greedy, stuff like that, right? So something more heuristic in nature. So it must be distributed. It must imply a limited intercell signaling. What we assume is like base stations at the macro level, they use some hard frequency reuse, because that's normally how it is done at the macro level. So in LTE, I think they tend to use reuse 1, honestly, but you would not have a very flexible way of allocating the spectrum. Okay, it's because the network itself is meant to provide some certainty in the service. You can't really fool too much around with bandwidth allocation for macro network. You have to provide coverage throughout the network for control purposes, for example. So this is kind of really the something that has to be there, okay, with certainty. So you're not going to change that too much. On the other hand, you can be much more relaxed with the low power nodes, because the whole point of it is you have to be adaptive to new situations, okay. You have new traffic to take care of. if you didn't have dynamics, you wouldn't need this flexible layer of deployment. You could just be using your macro deployment. So you are allowed to do things. It's also less standard bound, or at least less tradition bound, because macro networks have been there for a while, but you know, these new technologies, you can at least play with assumptions more, because you know, they're less established. For example, that's why for duplexing in macro networks you use FDD, which is kind of the what has been used so far, but they are actually playing also with TDD, full duplex and other things in the small cell layer, because it's less established in the standards also. Okay, so you can do more flexible spectrum usage for the low power nodes. Okay, yeah. Question? Okay, so this is just another representation, like maybe a clearer one, okay, about what I've been saying. So you have 3 bands, say, of spectrum, 3 parts of spectrum. Each one is given to one of 3 adjacent base stations. So you can think of like reuse patterns, right? Spectrum, like base station clusters. While the PBS stands for pico base station, okay, and MBS is macro base station. So this pico base station, low power node, small cells, call it as you want, doesn't matter. So they can use in a flexible way the portions of spectrum allocated. And they actually, I mentioned in a former slide, master-slave relation. The master is the base station and the slave is the pico. So we are going, at least in this work, our goal is to favor the macro if possible. So for example, targeting edge throughput drops in the macro network, okay? So basically what happens is that if you have interference, if the macro base station experiences interference for its users, it will send what we call an HII, a high interference indicator, to the picos, and it will tell, okay, now you have to do something because you're disturbing my operation. Okay, that's the philosophy, and it's very simple signaling exchange, so there's not really too much going on. You do have similar, actually. Sanjay is more expert than me in this LTE standard domain. I think they do have some signaling for, right, for high interference and so on. So it's not even that, you know, radical in terms of disruptions to the standard in 4G sense. So this figure is a bit crowded, but I'm going to, you know, walk you through it. So first of all, what are the axis labels? So on the y-axis we have the cell edge user throughput, so the outage essentially, and on the x-axis we have the average user throughput. Okay, then we have another thing. So you see we have 1, 2, 3. These are different arrangements in terms of spectrum allocation between the macro base station and the lower and the low power base station. So in the first case, you see you have a full overlap between the bandwidth used by the macro base station and the bandwidth used by the pico base stations. So we expect a lot of inter-system interference. In the second case, we reduce the overlap. In the third case, we remove it altogether. So of course, it's not surprising that the trade-off curve between outage and average throughput moves to the top right of the curve, because we are improving the interference situation the network sees, yes? Now, that though requires some signal in exchange between macro and base station. So if we change the spectrum allocation, it's because we have been told so. It's a master-slave protocol, right? So we want to avoid that if possible. So we have another degree of freedom, which is again coming from the LTE standard. It's actually the tuning of the proportional fair scheduling algorithm. Now, for those of you that are maybe from higher layers or lower layers, the proportional fair scheduling, so scheduling, first of all, in this context, is how you allocate the resources, essentially time frequency resources in LTE, to the users. That's pretty much what scheduling is about. So the base station will decide at every TTI, every time transmission interval, so every 1 millisecond will decide to whom to allocate these resources. Now, there are few things you can do. If you want to be perfectly fair, there is a strategy called round robin, which simply cycle through, right? You're given a chance to transmit regularly, regardless though of whether you deserve it. So what I mean is, like, whether you have a good channel or not, you're given it anyway. So this is perfectly fair, but definitely not efficient. On the other extreme, you have what we call maximum throughput or maximum carrier over interference. And this is where you actually do not care about fairness at all. You just look who has the better channel, you serve it. So if it happens so that the user has always the best channel, this user is always going to be served. So maximally efficient, but also maximally unfair. Yeah. So now we want both because fairness is important. You don't want any users to be excluded so that it complains with the operator about bad service, right? And you would like to have the average performance to be pretty good. So proportional fair is a response to this double requirement. And in fact, the metric based on which you allocate resources is essentially a ratio, where at the numerator you have the expected future throughput. So you estimate what the throughput is going to be the next time you will serve that user using that resource. Numerator. The denominator is just a log in a sense, taking into a log, I mean in a sense like an account of what has happened before, the history of the throughput for that user. So this is taking care of both efficiency and fairness, because the numerator is about the throughput you are going to experience likely if I'm going to serve you. So we want that to be high. Okay, we want you to have a good throughput. But on the other hand, we should be cognizant of how many chances you had in the past. So if you got a lot of throughput in the past, maybe it's time for somebody else to be served for the sake of fairness. So because you have this past throughput at the denominator, this will bring down the metric. So there is a tension, and you can even tweak things. It doesn't have to be a plain, say you have x divided by y. It doesn't have to be like that. You can start to have exponents. Start to have alpha, beta parameters that tweak you more toward this maximum throughput extreme or more toward this round robin extreme, right? And all the degrees in between. So that's what we mean by this proportional fair set 1, set 2, set 3. You see this PFS1. It's different sets of parameters for the proportional fair, which are more pushing toward efficiency S1 or more toward fairness S4 and all degrees in between. So what we do first, given the current spectrum assignment, we check, are we okay with the current situation? Are we okay means, do we cross the requirement threshold? For example, you have a threshold for average throughput and a threshold for cell edge, very simple system. So you have to be in the top right corner of this figure. In the other squares, you have a problem, either with outage or with average throughput or with both. So you check, am I there? For example, for the green curve, I'm pretty much always there unless I'm using the set 1. So for that case, I don't even have to communicate. I'm just going to actually change the proportional fair set of parameters without exchanging any information. It's going to work out. It's because interference is in a good place. On the other extreme, no matter what I do for the kind of purple-blue curve, I'm always going to be bad, no matter how much I strive to change my proportional fair parameters. So it's never going to work. So if you are in that bottom, say, situation 1, the only thing you can do is to send a high over high interference indicator to the pico cells and ask them to do something, change in the spectrum allocation. It's a very simple scheme, but I think it's a good example of the different factors that are playing a role, right? So you can actually literally move, across this operational plane and until you get what you would like to get. Okay, any question? Now, the situation can become even more complicated in the sense that now people are not just happy. The heterogeneous network is pretty much the 4G story. But in 5G, the picture has shifted towards something called dense networks or even ultra-dense networks. Okay, so what they mean by that is basically situations, you see where, so the situation on the left, you have one base station serving a few users, yeah, probably more, like maybe up to 50 to 100 nowadays, right? Then you move toward dense networks, which is where you have a comparable number of small base stations and users. Yeah? And then you have alternate networks when the picture you had on the left is completely reversed, and you have actually users that are less, maybe way less than the number of base stations, which is something a bit different than what we have nowadays, right? Very different actually. So in the past, I told this before in this course, in the past the situation about scheduling resource allocation was always keeping in mind that users are cheap and resources are scarce and expensive. Yes? So users have to strive to get something because they have to share resources essentially. So resources are the scarce thing. So a base station, spectrum would be what you have to kind of manage with care. But users, as many as you want. They are the ones that have, they are at loss in the system, so to speak. Now the picture is reversed because if you have an alternate network, it means that the user becomes the expensive resource, so to speak. Users are few, so the different access points, if you want, have to struggle to get that user to serve. You see, I'm making it a bit human, but of course it's technological, so there are algorithms, nothing personal here, but just to give you some understanding. So I don't think there is still so much work on that, but I suspect one thing that will happen if these alternate networks is confirmed, because right now I don't think it's really deployed, it's more in papers. It could be that the resource allocation problems change in a way that the allocation so it's kind of you have this reverse situation where you have to decide which base station to allocate to a specific user, for example. Okay, so it's kind of reverse scheduling if you want. Yeah.
One thing is that from this figure we can see that number of base station has been increased.
Yeah.
Okay. So how the base station interference can be managed in this particular network?
I think it's a very complicated part of the story. So one way is similar to what I just showed, is like to use self-organization. So I think you have actually techniques like agent-based modeling, game theory. They are about taking distributed decisions. So you do not need a central genie. So you just observe the environment. And for example, let's say I have some work I'll show you in the last module where we had this similar problem. And what you do, you apply a simple set of local rules. For example, you just check what the neighbors do, and you don't do like that, right? So you are going to see, let's say you have 5 channels available. So you're going to ask to check each of the neighbors which channel they use, and then you would pick the one that is least used, maybe not used at all. So this is kind of very much distributed, but it kind of works, and the communication is almost inexistent. In a sense, it's passive. You just, for example, you could literally have, you don't even have to ask. You could just listen, right? You could do a bit of sensing and check who is using what, and you do differently. So cognitive radio, these kind of things are there. I think at some point you might have to give up orthogonality, so you can do things from 5-layer viewpoint. We saw the waveforms, right? Maybe OFDM is not the way to go because it requires too much synchronization. Access, maybe you don't have to do scheduled access. You might have to do contention-based, ALOA, stuff like that. So there are, this is part of the discussion. Yes, it's a very good question.
So another thing is.
Yeah. Yes. Yeah.
How much mobility this type of network can support?
Mobility is complicated because you have already, it's already difficult enough, right? Like that. I think you might have, again, it's not there. One thing you could think of doing is to have, my suspect is that you might have to go back to Manet. Mobile, I think so. Actually, we do have, I don't know if Aritra, Debjan is there, so you know what I'm talking about. We just had a discussion, right? So it's with Professor Das and Aritra. So I think these are all good questions because in fact they correspond to possible research coming up. I don't think there is still too much because there are still many problems to be solved in the static way. But for example, I'm thinking if you go into things like vehicular networks or drones, this is a situation that is relevant. You have a lot of stuff, a lot of base stations, dense, in an area densely deployed, but they can also move around. But for example, I have another project with Nokia in Ireland, and again, it's similar in this space, but we are taking baby steps toward mobility because it's a very difficult problem. For example, one way to cope with interference is to use beamforming, okay? But the more mobile is your device, the more difficult. It's really like if you write down the equations, trigonometry becomes a nightmare. So it's not so easy to cope with. On the other hand, I'm just putting on my researcher hat. That's good. If it's a non-trivial problem, it's actually something it might be difficult even to anticipate the outcome of. That's normally a good topic for a PhD or a research project. If you already know whatever will happen next, that's development, right? Which is still valid and challenging, but it's not research, right? So the trick here is to get things you can solve. So you have to have some intuition, at least theoretically, should be possible. So you shouldn't come up with a problem that is so difficult, so complex that there is no hope. So I think the vision can be grand and can be ambitious, but you have to have baby steps. So I think it's very good, in my opinion, when there is a tension between the final result being unknown, possibly completely unknown, but you have to know what the next result is going to be in 3 months. That's where research is going to work, right? Sometimes I see sometimes the people getting wrong the parameter set. So they might get a sequence of steps and they exactly know what the steps are, but that's what developers do, which is fine, but it's not research. Or they might start to be dreaming. A lot of sketches, a lot of fluffy things, a lot of ambitious, but that's not research either, right? So that's storytelling. So you see, keep in mind you don't have to know the end, but you have to know the next step. If you keep having this tension and pushing forward the frontier of the unknown, that's how you push forward the scientific research, right? That's true for any field. So I think ambitious problems are very good, given that you know how to handle them in the short term. Also pragmatically, every one of us has to report back to somebody, myself, the president probably of the university, everybody, right? So you can't just make up stories, right? And that's bad. On the other hand, you can't have a complete lack of vision. That's bad too, right? So as long as you keep this healthy tension between short-term objectives, next paper to write, next report to submit, next exam to pass, you have to have a plan for that. But it would be very sad and dull if you had a plan for every single month from now till you die, right? So I think you have to keep an open-ended set of possibilities. Yeah. Okay, so very interesting problems in this domain, and in fact, I think the motivation behind many new tools is due to this kind of problems, actually. Any other question? Yes.
One thing is that if I want to use the self-organizing technique, so by using game theory, so I need suppose I am thinking from one user perspective and I need the other user's channel condition, every user's channel condition. So how the signaling overhead can be reduced?
Very bad. I think that's not going to be scalable beyond some point. You do have, now I'm not a game theorist, okay, I can get in touch with people that know about the field. Definitely they are very, very big experts. What I understand is that game theory is a set of families of techniques. So you do have things called incomplete information game theory, so where you can actually operate based on minimal amount of information. So you don't have to have the full picture. You can start to have incomplete information games also, right? And
but in the case of game theory, I have to choose one policy, depends on the other's action. Okay.
yeah, no, but you see the actions are, okay, there are results showing how the system evolves.
Maybe the distance of another users also. So whenever I want to get this user's position, particular location for at particular time, so I need the details information of the location of each and individual user.
Maybe yes, but you also can get away with aggregate information. I don't think maybe you necessarily need very precise information. A lot of things, for example, are done based on statistical information, like correlation of the channel. So you do have different degrees of the information you require. I don't know if there is anything like blind game theory, might be. So, but you do have actually, it's like for channel state information. You don't necessarily operate just with full, right? You can get away with lower amount of information. So the information you need from the environment varies quite a lot with game theory. So again, I'm not an expert though, but if you have any specific question or interest, you just let me know. This is true for all the people in the room and any topic in the course. Or you might have gone to the website of my website or my research center website, and then feel free to contact us. Okay, we don't promise immediate response, but we do promise a response. So if you have any curiosity, want to know more, get access to papers, let us know. I think that the main purpose for me being here teaching a course is not to give you 20 hours of generic knowledge. This is what this course is about. Okay, it's like a primer, get you to know a topic. You say, okay, sounds interesting, I'll look more into it. That's all this course is about. But it's
What may be the power required for the picocells power
yeah,
to transmit the
yeah.
signal?
So
What is the required power?
it's so I think it's something like it changes. I don't know if there is any specific required number. I remember something like, let me think. So it's like 40. Yeah, it's 1 watt, something like that. So it's like 43 dBm is for macro, which is like 20, and then it's the equivalent. I don't remember now in dBm, but it's something like it's 1 watt, yeah, or fraction. Can also be a fraction of a watt. Yeah, but it's an order of magnitude less at least, or 2, than the base station. Yeah, so it's a small one. Yeah. Okay. Good. So the system model we use is pretty simple. So here I'm going to talk about the case where you have a lot of small cells. Okay. Reuse 1, all the cells are using the same bandwidth B. So the purpose of this is that we do not want other effects to play a role. We just want to have the plane situation and see the performance limits. Based on this, we will give suggestions about what to do with the spectrum allocation. But first of all, we remove the spectrum allocation from the picture. We are just interested in seeing the effect of topology here, okay, of the deployment density. Single slope path loss, which simply means you have one path loss exponent. Fully loaded network, it means that every base station is active. It has at least a user to serve. Full buffer traffic, it means any resource you're given as a base station, you're going to use it, or as a user, you're not going to spare any capacity, and you're going to connect to the base station providing the strongest signals. These are all assumptions, especially the one about full buffer and full loaded network, which are again in the same spirit as using reuse 1. We do not want any extra factor to play a role. We do not want to say throughput is low because maybe traffic is low, or right? Or that's not what the goal is. We just want to say, okay, given a set of conditions which is in a sense not weird or not special, what is the impact of topology? That's the reason of these choices. The metrics are very simple. You're familiar by now with the spectral efficiency. We saw it before. You divide the throughput by the area by the bandwidth. Energy efficiency is the first time I introduced it, but it's very simple again. Throughput divided by power. Okay, so you just are going to account also for the power consumption of your network. What is power? We're going back to that because there's not just one answer. Okay, so we have some studies that's actually 5 years old now, so a letter where we studied what happens in terms of the area spectral efficiency. So we found actually we proved that if you have a density lambda of base stations, so lambda is the number of base stations per square meter. And you have some seed power P0, and you have a path loss exponent which is greater than 2, you can actually prove that this is the best thing you can do in terms of power allocation, because it's going to guarantee an area spectral efficiency gain which is linear with the increase of the number of base stations. So I think I have a figure. So this line here from the bottom left to the top right, it's actually the area spectral efficiency, and we proved that if you have that expression for power allocation, you actually can guarantee this, but with the minimum possible needed power. So it's just the best thing to do. You're not going to waste power, and so if you use more than that, you're going to waste power without changing the behavior of the area spectral efficiency. If to use less power than that, you're going to get a drop in the behavior because it's not enough power. So this is just the right power, just about the right power. Okay. Another consequence of this result. So there is the paper here if you want to check, and I can also share the PhD thesis, which has the whole story about this small cell at heterogeneous networks. So the work I'm talking about today, and also in the stochastic geometry unit, they are all part of a PhD work that was actually done by a good student of mine over the past 4 to 5 years. I don't know, Sanjay, if you met Carlo. You met. This is Carlo's work, actually. Okay, so basically, yes, because you had some overlap, right, between you. Yes, so you know the guy. Okay, so basically, you can compute, of course, the total power over. You just have to kind of take into account the area. So this d squared is now the area. So you have lambda times d squared means you are kind of integrating, right? And you get the power you consume over all the network. And what happens to the power, interestingly, is that it goes down. So you become this is kind of the power, not only that gives you this expression, this p0 lambda to the minus beta half, is not just giving you the linear increase in aerospectral efficiency, it also gives you a good power consumption because you are becoming very efficient in terms of your own throughput, but also in terms of the interference you create. It's just the right value. Okay. So, for example, if the density increases by a factor of 8, the total transmit power decreases by a factor of 5, which is very good in the context of green networks, sustainability, and so on, right? Now, there is a big elephant in this room, in this slide at least, which is the assumption of a single slope path loss. That's not a realistic model, okay? And we are going to see how things change removing this assumption. So, in terms of energy efficiency, well, what we did so far was mostly the transmit power, so the power you radiate from your antenna. Any question, Dabjani? No. So no, that's not the only source of power. In fact, there is a paper. I think I mentioned I mentioned it in this course before, right? This wireless communication paper from 2011, when they do a nice study of the power consumption of a communication network, and in fact, the largest part of it is not due to radiated power. It's due to processing power. It's due to the power that you need just to activate a base station without even transmitting, right? So that's the biggest part, and it's what we call, actually there is an unfortunate choice of notation because the P0 before would be P1 now. Anyway, so you have a fixed part of the power, which is due to signal processing, the powering up of a base station really, without doing anything, and then PTX is the transmit power, the one we normally work with as radio engineers. So you can do a bit of math, not too complicated, and you get actually the expression for the energy efficiency, which is fairly simple. So you have some throughput value for a certain density, you have the fixed power due to the signal processing, and then you have to have a power which has to do with the density, because the density is everywhere, but eventually you will see just in one term at the denominator. Okay, now this is the math, might not tell you much, but the result is interesting. Because what happens is that if you take the limit for density going to infinity, you actually see a monotonic behavior of the energy efficiency. So in the beginning it's very low, okay? Then it's going up and then it saturates. So what does it mean? It means that if you have too small a density, it's kind of not making sense to activate even the base stations. Because you are kind of wasting power. You are not serving really too much because you have too few base stations, yeah? And then it goes up and up and up, and at some point it's just saturating. Why? Because at some point it's the other way around. So for low densities you have a throughput problem. For high densities you have an interference problem. So you are wasting energy in another way. So before you're wasting energy because you're just not coping with the throughput anyway, so you're better off just not using the network. On the other extreme is the problem is that you are actually wasting energy because you are just generating interference. It's just too many base stations and you are using power for the sake of it. So again, you will have a cap. Now, intuitively, this shouldn't be like that. I would expect that for higher densities, it should go down. And in fact, it's true. This is just an artifact coming from the simple channel model. That motivated another bit of research I'm going to talk about soon, and it's based on this more realistic model. Okay, there are a few things, a few ways you can model this double path loss slope model. Essentially, you will have some component of the path loss which has to do with line of sight, some component which has to do with non-line of sight with some probability. It's like a Bernoulli distribution, yeah. And the probability of being in line of sight or non-line of sight has to do with the distance, as we see on the left plot. Of course, the more far away you are, you would expect to be more unlikely to be in line of sight, right? Because some point you're just too far, and obstacles and other things will be there. So this is a model taken from 3GPP, very nice one, very very useful one. And here you have a plot to show how the path loss goes. Of course, low line of sight is heavier in terms of path loss. Okay, so but you have basically a probabilistic model now for the path loss, right? Normally, the path loss we are used to is not probabilistic. You get an expression which is actually dependent on the distance, the path loss exponent, the frequency, but it doesn't change, right? Given an environment, you're given the path loss expression. That's what we call single slope. Now, multi-slope have a probabilistic component, okay? I'm going back to this. This is just a qualitative thing of what would likely happen. So if you increase the cell density and you have a more realistic propagation model, which has both line of sight and no line of sight possibilities, you will see a big gap in the energy, in the area spectral efficiency, and you start to see strange things. Superlinear behaviors, sublinear behaviors, you see all sorts of things. It's not this straight line anymore. Energy efficiency is actually not going to be saturating, it's going to go down, as we would expect, because you're just wasting at some point your power to create interference. Okay, and there are other even weirder things like outage and spectral efficiency. So without the area, in a normal single slope path loss model would be constants. They have absolutely no relation with the density, which is again not right intuitively. I would expect my spectral efficiency and especially my outage to be very much changing with the density. If I do nothing with the frequency resources, with power, with beamforming, with processing, interference cancellation, I can't just expect deploying an infinite amount of base stations that outage won't go down, because interference, in the end, when you densify things to the extreme, one axis point will be good, and then infinity will be bad, all interfering. How can that be not impacting outage, right? So I think that the reason why we went into this multi-slope path loss model is because intuitively there was something wrong. Some good information was there with single slope, but not the full story definitely. So that motivated some further research that I'm going to talk to you about in the next few lectures. Okay, any last question before we take a break? Yes?
Does this path loss models is applicable for 5G cases, right?
No, we have an expert in channel modeling for 5G is going to tell you more about that aspect, but I think, so okay, one thing also I want you to take away from this course, I was discussing this with Professor Das, it was his opinion, and I think it's a correct one. I think we should also move away from 4G versus 5G. It's more releases. It's a continuous deployment of releases. Now you have release 15. LTE, we started talking about 4G with LTE, probably what, release 10, possibly 8 to 10, something like that. And then in between you have 4.5G, and then, so I think, that's the right way to go. So I think 3GPP, yes. So 3GPP is kind of what defines these releases, at least for the mobile broadband. IoT, machine type, another story altogether. I'm just talking now mobile broadband. Yes, I think you can use it for 5G because it's still 3GPP. Now, what we found in our work is that this model, as you might guess, this expression is nasty. It's highly nonlinear, minimum, exponentials. It's a bit difficult to manage mathematically, so we kind of found an easier expression, which is an approximation, and it gives much more manipulation power with math. But definitely anything that is following the 3GPP recent releases is 5G compliant. They are the ones calling the shots for 5G. Okay, so this is 5G totally. Okay.
This model does not include any multipath methods.
In this work, not. There are two reasons, I think. One reason is it complicates the math. Okay. Another reason is that we are not going to assume a too large mobility of users, because normally small cells are about serving indoor stable traffic. You are not going to use small cells to serve a highway or a very mobile situation. But I think when you go into the more analytical version of this work, you use stochastic geometry. Definitely shadowing is kind of there. I'm not too sure about fading. My experience with fading, though, for this kind of indoor static environments, it doesn't play such a big role. I mean, it might change, let's say, it wouldn't change the relative behaviors of curves. So if a system A is better than a system B, if you add fading, it's the same, it's just it scales things. So for comparative reasons, it doesn't change too much. Of course, if you start to go into vehicular networks, outdoor mobility, then it's important, yes. It normally, I'm even thinking, it's not true actually the math becomes so nasty, it's just that the effect is not so big. That's normally you go a long way with path loss and shadowing, at least for lower mobility scenarios. Yeah. Okay. So we take now a break, and we are back in about 10 minutes for Professor Kumar. Actually, this is not the right one even. Oops. Yes, that's the right one. Okay, so I think we did this. Am I right? Yes. Right. Okay, so what we basically do today, so we did see a bit of this thing. So we did see a bit of the spectrum sharing, license spectrum sharing, so which is the approach apparently in the latest perspectives on 5G is emerging. We saw something on Cloud RAN, right, distributed RAN. Now we are going to see how they kind of can be considered together, okay, and they have they lead to a richer space of trade-offs. So yeah, again, these are different things compared to what we are used to up to 4G, because up to 4G the story was pretty much either you have a licensed spectrum or you do have unlicensed, and cognitive radio was sort of still in essence licensed in the spectrum, I mean, itself, because you are going to sneak in and you are not requiring a license, so you are using it as if it wasn't licensed, but in fact it's licensed spectrum, and you are trying to just not disturb the rightful owner, right, of the license. Or you have Wi-Fi, which is completely unlicensed, right? You don't need a license at all. Now that's changing in 5G, because you have these in between spectrum sharing regimes where you have actually subletting, right, of licenses, and you might actually acquire the right to use a license for a shorter period than the current licenses, maybe a narrower area, in agreement with the incumbent that actually is the primary owner, right? And that's in between license and unlicensed. That's why they call it something else, license shared access. Cloud RAN is about separating the functionalities related to RF and the functionalities related to baseband processing, possibly MAC, and you decide what to put at the edge of the network on the remote radio heads and what to put in some unit that does the processing. And you can start to play with distributing these functionalities, right, and so on. So now we are trying to see how all of this comes together. So first of all, we have to, I'm not a big expert in business and like the value chain, but something probably we have to start from is like you can actually associate value to different items of the communication network, and you do have things like we are well familiar with, like licensed spectrum, radio access network, backhaul to some extent, a bit of core network we talked about. The rest we didn't really talk about, right? It kind of goes beyond the point of this course. So you have, for example, value-added services like applications, content. You have the pricing aspect, right? Billing and so on. You have actually the offer definition process. So it's what you are actually going to offer to the customers as a product. So for example, when they send you they sell you a bundle, right, of data, voice, and so on. And eventually you also have the marketing, right? This is it's not really technical. This is like more of sales, right, approach. So how you're going to propose yourself, right, as a company selling something. Okay, so for example, one thing that is emerging is the concept of virtual operators, so mobile virtual network operator, MVNO or VNO sometimes in brief. So you're basically not bound to be buying, I mean, to be owning all of these blocks in the value chain. So for example, you could own the right hand of this arrow, but you could essentially rent the left half, okay, the left part. So you might not need to own the spectrum yourself. You might not need to buy very expensive chunk of spectrum at an auction, spending a lot of money for a lot of years. But you might actually use spectrum which is license exempt. So for example, one approach is this license shared access. So you're going to spend a smaller amount of money because you're going to not to buy the license for long term, but you're just going to kind of they rent to you the spectrum they own, okay, something like that. Or you might actually think of like the approach they call LTE unlicensed, where you actually can use unlicensed spectrum even, you know, without even subletting or anything. You might not need to have a, you know, radio access network, which is very expensive, you know, with base stations and all that goes with it. You might actually think of Wi-Fi itself as a possibility to deliver content. There are actually community services, like they serve, for example, a municipality in terms of wireless network, and they use actually Wi-Fi. So there are stuff like that in, I think, in Sweden, for example. Okay. So and so on. So in backhaul, for example, you might think of alternatives like self-backhauling. You might use radio itself instead of, again, laying fiber. So these are much lighter, if you want, ways to achieve some of the functionalities in this block, okay, chain. So in the past, the traditional operator would have to own all of this, and each operator would have a different package of the same things. Nowadays, so you have, first of all, different alternatives how to get things. You might buy them in full, you might rent them, you might not pay even anything. And another thing, you kind of give up the exclusivity of the ownership for the purpose of cost and efficiency, and that's sharing. So that has already started to change with the first works on spectrum access, sharing, cognitive radio, and now I think it has advanced quite a lot, the discussion in that sense. Now, another thing that is becoming apparent is the concept of resource is way broader than it used to be. Okay, so it's not just spectrum, and okay, let's say traditionally what we call a radio resource is probably what? Spectrum, power, and not much more really. Might be codes if you have CDMA systems, but space and power are kind of the same thing, and time is kind of there, but that's it, right? So now you have many more things. Okay, you have things like, well, we start to see that, as I said before, one resource you can play with in these dense networks is the base station itself. You start to decide to switch them on or off, deploy them. So what before was kind of just something that was there and you were going to use without changing anything, now you start to have much more, it's much more of a resource, right, than an enabler to the use of resources as it used to be. Even backhaul, if you think about it, if you start to have things like self-backhauling, where you use a wireless link, again, you could decide to use more bandwidth to do the access or more bandwidth to do the backhaul. So the backhaul itself, right, or actually frequencies. If you change the frequency of usage, you might again play with the kind of resource you have in terms of backhaul. If you use millimeter wave, you are considering a backhaul of a different kind than if you have a lower frequency because of the propagation characteristics. Storage, now, I mean, things are definitely becoming very popular in this domain, caching, right? So memory itself, I mean, honestly, I think I'm not wrong in saying communication engineers never really considered that up until a few years back. It wasn't really in the picture, right? It was about communicating things, not storing things. Computing, processing, with all of these cloud services and, you know, IoT things and distribution of functionalities, Cloud Run. It's also about computing now. So again, communication engineers wouldn't know what happened to this data. We'd just be transferring information reliably and fast. Now it's also important who does what, in a sense, right? So this, you see, all of these things are actually making the picture of resource and resource sharing much more intricate than it used to be. So for example, you could have actually a situation where you have, say, this is just for the sake of example, so you might have massive distributed MIMO, so you have a lot of remote radio heads, which pretty much just receive the signal and, you know, might sample it or not, and they send it on to the central unit doing the real baseband processing. This is not much more than that, okay? And then you have the centralized baseband processing center, which does the real baseband processing. And here, for example, you could have services like, say, Netflix, like you know, on-demand video delivery platforms, and machine-to-machine that could use actually, they are oblivious in a sense to what happens here. They do not own that. They just tell, in a sense, to the central unit what they want, okay? And so there is a, in essence, and they totally coexist. So you could have Netflix, which is the red boxes, could use some baseband units and some red antennas, while at the same time machine-to-machine might use others. So that in the past, you would, I mean, to deliver a certain service, you would have had an independent network, right? Nowadays, this is not true. So the concepts like virtualization, slicing, they're becoming very popular because you have the need in 5G more and more to serve with the same network very different services at the same time in the same area. So the only way you can make it sustainable is to have more flexibility in the way you define and allocate resources. Yeah, sounds like a bit vague, but there is actually a good bit of work, and it's a well-defined engineering problem. We are working on that among other people, many other people, and I would take the point, this is still a bit abstract, but we are working toward making it more concrete. So you would have actually well-defined optimization problems tackling this, okay? And it's essentially, if you want, the simultaneous operation and possibly deployment of networks, kind of, you know, overlaid one on each other. And the concept of flexibility and dynamics become very important because you have to be flexible enough to change according to the requirements, but it takes also time. This might lead to very complicated, actually, if you just want to see it from the signal viewpoint, very complicated interference management, right? Because it was already complicated with just one service. Now you potentially have actually, and there is no bound, huh? You could think of this for 50 services, right? It doesn't have to be 2. Time scales, how much time does it take to reconfigure the thing? So these are challenging problems. Now, the way we see it, in essence, the resource management and sharing up to, let's say, maybe a few years ago, it's been about this, serving the single users, okay? I have a population of users and I individually take care of each one of them. Now the picture here, because of this, you know, much broader actually picture, it cannot really be that way, and you wouldn't have probably the time to, you know, change per millisecond how you map resources to a service, right? It's even, you can't think of that, right? So because we are already at the edge for a single service, you can't possibly add, say, 10 networks and pretend that in 1 millisecond you do the same thing. So you have to go a bit broader in terms also of the time scale. Possibly you have to think population of users. It's more that the allocation is kind of another layer of resource allocation that takes care of the services. Yes, so you see that the problem we had even with the resource allocation becomes more complex actually, but it's probably a requirement because I mean we do not choose what the requirements are. It's the United Nations essentially, ITU, and they want these different services. So it's not that we do it because it's cool. We do it because they asked us, right? So machine to machine, critical IoT, mobile broadband, vehicular networks, and whatnot. and you know, we have to accommodate all of them. And again, it's not, we can't think every time a new service comes up to come up with a new network. It's not even economically feasible, right? It doesn't make any sense. So there are a lot of new problems actually coming up in this sense. Without going too much into detail, LSA, I think I said a bit before what it is. So so the architecture is something like you see on the top right corner. So you do have an incumbent, like it used to be in cognitive radio, and you have now a difference compared to the traditional cognitive radio is the concept of repository or database, right? That was something that was introduced. So you do have information about, for example, the usage of the incumbent of the spectrum over a certain area per time. You might have actually rules that come from the national regulatory authority in terms of power levels, in terms of how far you can transmit from the incumbent, all of these things, right? So combined, they give a picture which the, what we call the license shared access controller is going to take care of. So this guy is the one that is actually getting the portions of spectrum that is then going to allocate to the specific network. So if you want, you could think of this multi-layer resource allocation where LSA controller is not about doing the user scheduling. That's taken care again by the way we did things so far, but this is another layer you add. So this guy is at a higher time scale, longer time scale. It will essentially negotiate somehow with the incumbent and the regulator the amount of spectrum it can grant to its own network. And you might have, we'll see later, many of these controllers, one per network, okay? So this is another level of scheduling you're adding to your problem. Yes? Yeah, they are considering mainly 2 bands for these things. In Europe it's 2.3, 2.4 gigahertz. In US it's 3.5. And in US they have this incumbent, this, let's say, secondary networks that, you know, strike a deal with the incumbent essentially. But in US they also have the cognitive radio story in the picture, the original one, because they have a third layer of systems called GAA, Generalized Authorized Access, where it's essentially like cognitive radio used to be. No guarantee of quality of service. You rely on sensing, and you actually operate as long as you don't disturb the layer 2 and 1 of this sharing architecture. So I think a lot of the things we did with cognitive radio are still relevant, but they are just recast in a new setup in a sense. Okay. So there was actually some discussion in the first week of this course whether cognitive radio is still relevant. I think so, but it's not relevant if you just do not acknowledge the changes that are happening in the application of cognitive radio. So I think if you can put them in the context of things like LSA or SAS is the equivalent in US, or LTE unlicensed, there are a few versions of it, LTE Fire, so that there are 4 like variants of this unlicensed usage of, so this usage of the unlicensed band for LTE. So these are new dynamics that weren't there 10 years ago, okay? 10 years ago it wasn't like that. So I think if you want to do good work on cognitive radio nowadays, you have to acknowledge that the framework is changing, and then I think you have to acknowledge you can't rely on sensing alone. Sensing is at best a helping hand, but it's, if you have to pick between database and sensing, pick database, because you see the dynamics you're dealing with are not at the same scale. So sensing could help you in the traditional resource allocation, which involves one service, one network. It can't possibly do the job for such a large area where the time scales are higher. So it's more important then that you have kind of the idea of the long-term behavior of things, which is what the database is about. So you see that the picture is changing. So this is a more comprehensive version of an architecture we proposed in a European project I was involved with. It's not the standard one, or I think it's compliant though with ETSI, this with the European telecommunication standard. But yeah, there are other versions of it. So you see you have essentially a few things. So you have, you still have sensing. You might actually think of sensing networks providing sensing as a service. They sell their sensing capabilities to somebody that pays. You have incumbents that are required to share information with the repository. By the way, a question that was there in cognitive radio is why should the incumbent do it? they don't have to, right? They bought the license. Why should they do it? Now, there are reasons, of course, of technical efficiency and so on. So what they are doing now, they are becoming smarter, also the regulators. They are forcing the incumbents to do it if they want to keep the band. So these incumbents are, for example, like normally government entities. You could say they use radars. Another example is, I'm thinking, like TV operation, okay? And they are highly inefficient, okay? And of course, there is a social function, and that's why they use them. But what is happening, at least they're trying, the government, to convince them that if they want to keep them, they have to allow for sharing, okay, when it's not critical, where it's possible. Now, I'm not fully aware of the actual implementation. Definitely, it has been tested, okay? There are proof of concepts, test beds. I just don't know whether eventually the system is operational, because still you're playing with bands that are a bit critical, but these are the bands they are considering, also in US. Okay, so then together the database and the sensing, say, part, they form a radio environmental map. It's kind of a map of the spectrum usage over an area and over time, and then it interacts with things like, for example, this LSA band manager is kind of a higher level scheduler that decides what portion of band goes to which operator. So on the left hand side is licensee. That's the name they use for these new sharing schemes. Before it used to be called incumbent and like primary and secondary. Now the wording is more incumbent and licensee, licensed and licensee. Licensee is like the one that pays a fee. It doesn't buy the license, it pays a fee to use it, okay? And there are some agreements, for example, about evacuation. So the incumbent still has the right to claim back the band. It has to give some time to the licensee to clear the band, maybe 30 seconds or so. And then this goes back to the original owner, okay? There are rules so that the incumbent doesn't do that all the time, so that's what the policy is about. Okay, spectrum is fine, we discussed this, okay? Even the schemes we already discussed before, but how about other, infrastructure? How about other resources, say infrastructure? Because it's not the spectrum is not the only expensive things. In fact, if you look at the cost overall the network, I don't think spectrum becomes the biggest part of it. It's expensive, yes, but consider a national telecom network. Would you think the spectrum is really the most costly thing? It's costly, but not the most costly thing. To deploy the infrastructure is the most costly thing. Okay, so to each of these base stations, and there are many. There is one every mile also. Easily in the order now, I don't know in rupees, but I'm talking dollars, $1 million easily, okay, or that region. Say maybe, let me think. More realistic estimate would be between $100,000 and $1 million, something like that. Depends on the capability, and you multiply this by, and this is just the base station. Then you have to lay the fiber, right, and there is all the cost associated with deployment. You have to send people around driving and measuring things like these drive tests. You have to maintenance, right? It's not just capital expenditure, capex, it's also opex. You have to operate the network, you have to repair it, right? All of this, this is all on top of spectrum. So you see, sometimes we get obsessed by spectrum as radio engineers, but it's not the only thing. So eventually, it makes sense to share things, okay? You might not like it in the first place, but it's definitely making sense. If, for example, two networks are serving the same area, maybe it's not a bad idea. Maybe what you could do is to share the mast or even the antennas, provided that, of course, you don't interfere with each other. Maybe yours actually, as two operators, would probably be assigned to different bands. So they could even be co-located physically, as long as they have different radio bands, they are not going to interfere with each other. Okay, so that's kind of things that people are starting to think about. So again, going back to the example we did with Cloud Run and LSA, you could think that actually the real separation happens over frequency, and all of this pool of antennas that are remotely deployed are actually shared, and they are just open for users to different networks if you want. Okay. Another thing you have to consider is if you start to have this cloud-based signal processing, cloud itself is something you can buy. You don't need to own the cloud. You can just ask to who does it well. IBM. You can just ask IBM to do it for you once you tell them what you want, right? So the paradox here is that you might operate a network without owning anything of the network itself. You might not own the antennas. It could be an operator just for the antennas, providing that service. Okay. There could be actually an operator providing the service of the cloud, and there could be an operator providing kind of you know, a retail seller for bandwidth. So you could go and buy what you need on the fly in essence. Okay, you don't need to buy as it used to be everything. One issue also with that is that it didn't really work to date because it's not profitable. Operators are really facing big problems that are essentially to justify the huge investment they have to make for every new rollout of a network, because they don't make money out of it. Let's face it, you know, the cellular telephony industry is shifting toward other services. So they run pretty much the voice and the SMS, some browsing, some data, but the real money nowadays come from other services like social networks, content delivery on demand, Netflix, Spotify, I don't know, all those of you that use this kind of platforms, right? Video, music, and so on. And those guys do not invest anything. They just use the infrastructure, right? The bandwidth that is available. It's what they call over-the-top services, right? So possibly in the future, if you really want to operate a network, it has to be very much tied with the service. Right now, the operators, traditional operators, they run the physical substrate almost. It's like the pipe. But they are not the guys injecting the liquid, so to speak, right? They provide the pipe, they spend a lot of money, they do the maintenance because they have to, but they are not going to profit because very little money is associated with it. The real money is from guys that is, in essence, the users of this infrastructure are not the ones that deploy the infrastructure. The users, I mean the business users, okay? So you might actually have to rethink how to make it sustainable as an ecosystem, business ecosystem. You might have to identify where the business value is and change you know, the business roles accordingly. So possibly you wouldn't have an operator doing everything. You would have operators for different functionalities, and they would, you know, it's like a market thing. So they would meet, find out what makes the most sense economically. Yeah. Again, speculation, but to some extent these things are happening because you do have virtual operators. For example, in Ireland, we have some of these. I don't know in India if you have some of these. They do not. Some operators nowadays that are operational, they do not own much of the infrastructure. Actually. So a bit more theoretical about some results. Okay, we studied like a system where you have essentially a downlink situation. So you have basically you have so the antennas on the transmitter side are distributed. So these, even though you see they are all represented together, these antennas are in different places. So we are assuming they are coordinated, okay, which is a big assumption. And then you form a pre-coding matrix so that they act as a virtual memory, right? And then you have your users. You do need more antennas than users for the thing to work properly, and you do need channel state information at the transmitter. Okay, you could call this a distributed MISO, right? This is multi-input, single output, but it's distributed. Multi-user also, right? So you can compute the capacity of this system as with dirty paper coding, and you'll find out under some conditions this is a good estimate. So you have W is the bandwidth, K is the number of users, capital M is the number of antennas in this virtual array, P is the power you send to each user, and 0 is the noise power spectral density. Yeah. This bound is tight if the channel the channel basically, so the matrix that relates the virtual array with the users. So if you put it in a matrix, this bound is going to be tight if this is well conditioned, which means it's far from being non-invertible. It's a matrix that has a good situation in terms of eigenvalue distribution, so you can invert it. Okay, basically. Ill condition means you are either bluntly you can't invert it because the rank is not full, or you're getting close to that. Okay, you have some eigenvalues are very, very small, so it takes a little tweak of randomness to end up in a situation where you can't invert it. So here we are assuming that somehow the matrix is well conditioned. By the way, what does it mean well conditioned in terms of a MIMO matrix? It means that the different paths are kind of uncorrelated. The minute you have a lot of correlation, you start to decrease the rank. Okay, say you have you have a 4x4 channel. If you have a strong line of sight component, it might turn out that this guy in fact is a 3x3, and one is just the two maybe links are very correlated. So this is like having two completely dependent rows in the matrix. So you can't invert that, right? Because you would become a matrix with zeros in a row, right? Why? You have to compute again so I'm going back to step by step. So if you compute the inverse, you need to actually calculate the reciprocal of the determinant. The determinant of a matrix that is not full rank is 0. 1 over 0 is infinity. Okay, that's all I'm saying here in a nutshell. So the problem here, you are given some bandwidth which is shared between possibly different systems. You have number of users k, you have a number of antennas m which is also shared, and you have some power budget. So the idea is to choose the precoding matrix in this virtual MIMO array such that you maximize the total rate given a certain power limit. So what happens if instead of as normally happens where you own all the antennas and you own all the bandwidth? What happens if instead you put it in a pool and you actually have to you just have to access it along with other systems? So what would make sense in terms of this optimization problem? Well, if you start to rent things, you have to consider things that we didn't consider before, which is the cost of usage. Before you had the cost of deployment, cost of buying the spectrum, but once you incur that, it's like a fixed cost, right? I'm not an economist, but there is a difference between a fixed cost and a variable cost. Fixed cost is something you buy, it's yours, fine, done and dusted. Usage cost is different, right? It's a variable cost because depending on the usage, you don't own the thing, you're just using it. The more you use it, the more you pay. Electricity, right? Water, these kind of things. So this is the same, which is again new, at least in the context of telecommunication, because the business situation is changing, as I said before. So you will have some cost for using the infrastructure, which is like, say, the cloud, the processing of the network. You will have some cost per antenna. For each antenna you use, you will have some cost, okay, over time. And you will have some cost for using the spectrum. Okay, so these are all costs. So you actually go from a metric. So before, in this course we saw a few metrics already. We saw throughput, outage. They're all kind of variants of the Shannon capacity equation. And then we started to add area, but again variants of the Shannon equation. The first time we saw something a bit different was the energy efficiency, where you start to put the power. Now here we do something different again, because we are putting the cost in the picture. So now what we call cost efficiency is going to be the numerator, which is essentially again the capacity, okay? And then we have the cost at the denominator. So now you have to think what you should do. It's not just that you want to maximize, because you see, you might have a situation where throughput is going to be very high if you buy a lot of these resources, but then it might not be economically sustainable. You could think it roughly as the numerator is your revenue and your denominator is the cost. So the closer they get, the more the profit shrinks, right? You could think that you charge proportional to how much data rate you deliver. The more data rate you deliver, the more the users will pay, right? You are delivering them more service, more traffic. But on top of it, you have the costs, right? So the minute this efficiency gets lower than 1, you're in trouble. because you're paying more than you are getting from it. So you're at a loss, right? So you want, you see the problem now is changing. It's not just about providing a lot of capacity. It's doing it in a economically viable way, right? It's a different problem. So as an example of results we might achieve, just a sec. So for example, if you solve optimally this problem, you will have some curve. And of course, if you, for example, here now it's a multi-dimensional problem, so you can't really visualize everything. So here we plot against the cost of the spectrum. You will have different pictures if you plot against the cost of antennas, as we see. So, okay, so you have basically an efficiency. Of course, your cost efficiency will benefit by the cost being very small. Even if the throughput is maybe small, if the cost is smaller, in terms of cost efficiency, you are going to be high, right? But if you start to pay a lot, for example, to use the spectrum, at some point you might be better off not serving the users because you are just not making money. Like the efficiency is becoming lower and lower, definitely lower than 1 at some point. Now, if you say, so this is the optimal thing, okay, if you solve this optimization problem, you get that curve, this blue curve. Now, what if you don't do any optimization? You just say, okay, I have up to 50 megahertz of spectrum available and up to 20 distributed antennas available. So one approach could be, okay, I'm fine with a little bit of spectrum, but I use all the antennas. So what happens here, you see that the more so you get actually this red curve. So the more the spectrum costs, the more using a lot of antennas makes sense. So you are going to at some point meet the optimal curve, right? On the other hand, you could say, okay, I'm fine with just few antennas, 4, but I use all the spectrum I have available. So in that case, you have to rely on the spectrum being cheap. So the more the spectrum is cheap, the more you're going toward the optimal cost efficiency, and that's on the left-hand side, right? So of course, you can start to play with things, and again, we are fixing the price of antenna here, which is bears some importance here, right? Am I right to say normally you probably didn't see this kind of things before in communication engineering? You see, these are problems that weren't really there until you started to have this profit issue, multi-service. It seems to me it's more and more becoming one thing with service provision, the telecom network design. Before it was completely detached. Forget about that, give me spectral efficiency, right? It's kind of difficult to do that nowadays, okay? To have the full picture, you have to consider some aspects of economics. Another example is this dense cell deployment. You can't neglect the cost of deploying the fiber, which is done to a large extent to date. Nobody is doing that, almost nobody. They are just playing with metrics, and I got a good comment about hazard of electromagnetic radiation. I'm going back to that. So basically, let's say just considering the economic part, you can't simply neglect it, right? You can't simply say I'm going to deploy billions of base stations because it might be non-viable economically. Who is going to deploy that fiber? Can you do it? How much money does it cost? You see, so it's not just about maximizing the radio link efficiency. It's way more than that. And so the cost is a big part of the story. So you could do, now since you start to enter this business thing, of course you start to have things like that are business-like in terms of terminology and tools. So we already saw the cost in terms of the efficiency metric. You could think of auctions. You could think of an auctioneer, which is a resource essentially selling the antennas and the base. It's another kind of system that has a role to play, and they might make money doing that. It's like the auction houses, right? You have them everywhere, where they sell, right, things to the best offering guy. So this guy could become a new thing that essentially auction spectrum and antennas to the best offerer, right? The person that pays more. And then this is another cost you have to consider. So it's the cost of using it. It might also be the cost in this case of acquiring it via an auction. So these are all things you add, right? So we have a paper. I'm not going into the details because it's a bit complicated in a few minutes. But essentially, what you have you do share spectrum and antennas. We started from a simple case where the virtual network operators have the same number of users, same rate requirements, same budget. So it's a very simple setup. You could complicate this if you want. There are two phases. The first one is discovering the price of things. So that's a big problem. You don't really know what's the value of things until you start this bargaining process, right? So the price of a thing is not an absolute thing. It depends on what people, how people value it, correct? So for example, let's say the price of a car has a lot to do with the time where the car, so you could, for example, produce nowadays a car that was popular in the 60s. Now there might be considerations about, you know, the fad about owning antique things, but in general you see it changes with time. So the perception of what is valuable today is not what was valuable before. Now I bet if you go and buy some spices nowadays, you don't have to get a loan from the bank. If you were 500 years ago, most likely that's what you had to do. It was more valuable than gold probably, or stuff like that, right? Definitely very valuable. So you see that this is a big part of the story. You have to discover the price of things. So once you do that, then you assign it to the one that makes most sense from the auctioneer viewpoint, the guy that pays the most, okay? Okay, now some results. I'm going, again, without going too much into the details, because this is a very complicated part actually of economic theory, auction theory. So if you're interested in this, I know people that are more into that. As a side suggestion, I have the feeling this economics bit is becoming more and more important. So a good topic for further research or PhDs would be actually bringing in some of these aspects in terms of the role of cost and other things, like, for example, a thing we normally do is trading efficiency for fairness. Proportional fair does that, right? Now, fairness in terms of technical design is not fairness in economic sense, okay? So you do have what they call axioms of fairness. So it's a very complicated part of the story. You do have things like auction theory. For example, contract theory was awarded a Nobel Award a couple of years ago. So these are very relevant problems in economics, and you know, it could be very interesting to see how some of these translate into a telecom setup. There are people, actually there's a professor in Hong Kong doing great work on this. I'm not an expert myself, but it's becoming a relevant thing, okay? You would probably need somebody that understands economics. So it might be more of a multidisciplinary PhD, where you have like an expert from telecom side and an expert from economics side, because it's a very different field. So let's say you focus on the antenna price. So the antenna price is on the x-axis, and the minimum rate you want to provide to any user is on the y-axis. So what happens? If you increase the minimum rate you want to provide, is becoming more and more challenging. So you start to have these different regions of where you can serve different number of virtual network operators with the same resources. So you have, when the rate requirement is not so high, you actually have you can serve maybe 10 operators, but then you might have to compromise with 5, maybe 3, maybe at some point 1, and at some point maybe 0. You can't do it, okay? That's one thing. Another thing is, like, you have you see these colors. So on the left hand side, the color code of the map is antennas. So the hotter the color toward red, it means you are using more and more antennas in this distributed MIMO setup. On the right hand side, the color code goes with spectrum. So the hotter the color, the more toward red the color is, the more bandwidth you require, okay? That's what these figures represent. So what I'm trying to say is, like, if you check the color code here, what happens is, like, you see, when the rate requirements are lower, you are okay with using little spectrum for each operator to be served. Of course, the picture changes the more demanding the minimum rate you have to provide is, right? Same with antennas. So with antennas, what happens? Okay, if you have to serve a higher rate, you will need more and more antennas. right? Now, at some point, it's just not going to be enough because of the requirement, which is too tough. So you will have actually to compromise and serve less. And then you go into a region where actually you are okay also with lower number of antennas, just because you are relaxing the problem quite a bit. Okay, that's this side. How about this side? Because there is the price of the antenna, right, playing a role too. So the more you increase the cost of the antenna, the more there is the likelihood at some point you will have to use a lower number, just because it's too costly. Okay, right? And same with, let me think. Yeah, this is actually, it's dual with the spectrum. So here we are again showing the antenna price effect. So you start with some spectrum, say 5 megahertz, okay, per operator. At some point, the antenna is so expensive that it makes way more sense to reduce the number of antennas and increase the spectrum you use. Spectrum and antenna are dual. It's a trade-off, right? The more you use of one, the less you need to use of the other one, and the cost plays a role in driving this, right? They are not fully orthogonal to each other, not fully complementary, because you still need a unit of spectrum and one antenna. So it's like having two sets that have a very tiny intersection, but they are not disjoint, right? But by and large, they behave as if they were two different things. Of course, you know, not mathematically, because we know you need one antenna, you need 1 hertz, probably you need what? A resource, right, of frequency, okay? So, and I'm not plotting the antenna, the spectrum cost. So, for sure, it becomes much more difficult to visualize. It's a lot of things going on, okay, and but I think it adds many new dimensions to the resource allocation problem, okay, and it makes it interesting. So now one thing we have to do is to compare with benchmarks always. So what we do here, so this curve is actually you basically share the antenna, the spectrum in an orthogonal way. What does it mean? It's like OFDMA. You get a portion of the spectrum for each. It's not really, it's like static sharing if you want. And then here you are actually also sharing orthogonally the antennas. So you get a bit of antennas each, okay? Now that's not really that good because while it makes sense to share the spectrum orthogonally, in this case, because the requirements are symmetric, all the networks you're serving have the same requirement. So it makes a lot of sense to give them the same portion of spectrum each, right? You're not really playing with very dynamic spectrum allocation situation. But it still makes sense to share the antennas. Why shouldn't you do that, right? So that's why the other benchmark, which is actually this guy, always on top, this is the case where you share all the antennas and you have this fixed portion of spectrum per network, okay? And our schemes, like with the auction based, are kind of in between, and they, depending on the antenna price, they follow more closely or less closely the top benchmark. So if the price of the antenna is very expensive, it will actually make more and more sense to have a, let me think. So if the antennas are very expensive, you're probably going to limit the number of antennas you use. So you're going to be toward the case where you get just a few antennas. You're not going to share many because it costs too much, right? But if the antennas are cheap, then it makes a lot of sense to use as many as you can, and that goes toward the case where you are actually possibly sharing all of them. All of them are up for grasp, right? So, okay, I hope it makes sense. We have some, you know, we have a paper on this, and we do have people are doing more work. Actually, there is a nice magazine paper about this auction-based mechanism. So there is more work going on in my lab. Not necessarily something I do. Just I have like a paper or two, but I'm not really too active on this. But there are actually people that are doing it. Okay, a small comment because I got a good question actually about, okay, we are basically over deploying things everywhere. How about impact on human health? It's a $1,000,000 question. I think, I mean, what I said to your colleague is like, I think we had this discussion also in the first week, right? Who asked me about that? You, right? Okay, I think it's not part of the mainstream discussion. That doesn't mean it's not relevant. So it has actually appeared now and then as a concern, I think. And there are some papers, but if, I mean, I think it's fair to say if you just look into the scientific databases, this is not going to make it even top 100 probably of the investigated topics. There might be different reasons for it. Maybe the mentality we have is more of a technological mindset, so you are trying to optimize the performance of a system. And if it turns out that deploying a higher density of access points is a very good tool toward increasing the capacity. It's the best tool actually, because you get closer, you get transmitter and receiver closer. So it makes sense. Okay, we are kind of trained as telecom engineers to do just that, to optimize the performance of a system, right? And if we have to design a new one, it's just that the metric that we have in mind. That plus possibly cost, right? But it's basically efficiency. Okay. Now, does that mean we don't have any problem? I think the correct answer as a scientist is I don't know. I think there have been some studies showing some impact. There would probably be another kind of equivalent number of people that would say it doesn't because of the power involved. The powers that are involved are very small. They are normally smaller than a light bulb. Okay. On the other hand, I think everybody experiences when they talk on the mobile phone for a long time, they start to feel some heat, right? So something is going on, I think. And I think that, so there are two answers I gave to your colleague. Okay, you can't be doing research on everything, so I'm not sure I will have ever the bandwidth to work on it. But if somebody wants to do that, you have two things I think you should keep in mind. And one thing is like you have to have data. You can't actually propose personal opinion, especially when it's against the mainstream. You see, if something is well established and agreed, you can actually base your ideas on that. You say, okay, this was published, studied. I'm not going to tell you that the Shannon equation is valid. It would be ridiculous, right? I'm not going to convince you about that because I said, look, go back. I'm not going to tell you that multipath is good for MIMO because again, you know, I'll point you to 200 papers right away, right? But when you don't have a significant body of literature, you have to do it, okay? You have to, you know, kind of find a team, a project. So maybe some funder that could be interested in these kind of things is Ministry of Health, Minister of Health, possibly some medicine. I just don't see the telecom community funding these kind of things right now, okay, honestly. So that's one thing. Another thing is like so that's the research bit. Another thing is the widespread adoption. Even if there would be some evidence that this might be harmful, now this evidence didn't stop cigarette producers, right? That's still a big business. So now people know. Okay, so I think awareness is a good first step. So to make them aware, you have to have studies, okay? And you have to get somebody to fund this research. You can't do it alone. You need a team, you need lab, you need, you know, all you need to do research. So you will need like a funder, and you have to find the right sponsor, right, for this. That's one thing. The second thing, so that's awareness creation. The other thing is a bit of a social / business nature. So again, making the analogy with cigarettes, to tell to people that cigarettes are bad won't stop the people that want to smoke anyway. So you have to give them an alternative. So the question, maybe the deeper question, is not whether cigarettes are harmful, which we know by now, at least to a large extent. What else can we give to people so that they don't smoke, right? We should have alternatives. Okay, the problem is more than the cigarette. The problem is more than why we need 500,000 access points in this room. Why are people so obsessed by downloading things and watching things online? Now, maybe I'm talking against our own business, but you see, maybe the problem is that there is not a valid alternative. I mean, if people would read more books, maybe you wouldn't have the need for ultra-dense networks. You see what I mean? So it's a very complex picture, and ultimately, I think, yeah, that's one thing. So that would create less of a need of a over-deployment thing, and you still have to provide something that makes it maybe economically viable to be possibly more power efficient. So maybe one way is to become very power efficient, so you reduce the electromagnetic radiations, but the big operators, they reason in terms of profit. If it's more profitable for them to be less power efficient, they will go that way. Another analogy I can make, energy sources. I think nowadays solar panels, wind turbines, these kind of things are becoming more popular, not because people are more concerned about the planet. I don't buy that for a minute. Not the big corporations. This is about making money. They are making possible, they see they can make more money maybe with that, at least in some segments of the market. So you see, I don't think it's very difficult because it's a very complex problem. I think there is, the best way is to do, first of all, you would have to take care of the evidence that there is a problem. If there is a problem, there is still a social reason why people are so much about mobile phones and data, right, on the go, and you have to provide an alternative. And ultimately, you also have to, you will still have people, I believe, that even if you tell them it's harmful, even if you give them alternatives, they will still prefer to watch maybe videos or use the phone, right? It's a choice. So maybe then you have to become more efficient on the network side, and then there is some business considerations. Why should operators invest in that? They will do it only if they see a benefit of an economic nature. One thing we should also keep in mind, we are not, it's important that we take into account ethics, but we cannot ask science to do that. It's us that have to change the picture. So you see, I don't think it's fair to blame 5G because it does what it does. 5G is a tool. We could tweak 5G to do other things, or maybe get rid of 5G altogether, and that wouldn't change the problem. That is, you see, science is a tool. It's like the knife, it's like the atomic power, right? You can use knife to cut chicken, or you can kill somebody. You can use atomic power to create energy that is clean and safe, or you can create a bomb. And the same with 5G, right? You can use it for good or for bad. So I think science is neutral, and that's probably the way it should be. But you can, of course, policymakers, you know, and so on, should probably worry about that. But it's something that I can't say for sure why, but it's definitely not something that is mainstream. So maybe it's time to look into that. But yeah, you would need to go through the various steps that are normally there with the research. So you have to identify concrete problem, solve it, get sponsors, push it forward to policymakers, companies, make it viable economically. So at best I see, even if you start right now with this concern, it won't be sorted before 30 years. I think that's true. So in the meantime, if the most important thing, if it's really hazardous, is to find out. If it is hazardous, then I don't think you're going to change the way networks are designed for a while. You would have to make the current networks less harmful. Okay? I don't think you're going to slow down the deployment of things, but you might do a better job in containing the emissions, for example. It could be as easy as now you're adding masks, filters, because of spectral containment already in 5G, because of interference, right? But you could have even tighter masks, so use a tighter filter bank because of this. So you see, there are things you can do, but you can't do it blindly. You first have to be scientific and see whether there is a problem. If there is, then it might be time to start to think solutions. Yeah? Any comment about this? Because I know it's a kind of popular concern. It makes sense. I mean, of course, it's our health, you know, our family health, right? So people would be very sensitive about this. But it's probably, if you are concerned about it, you should take action, because I don't see that coming from the academic circles or industry. It's not on the agenda. As simple as that. Okay. So it was a very long morning. I think you must be very tired. Thanks for the patience. We are going to have the demo session, Sashank. Where is Sashank? No Sashank. Yeah, I think it's a 3. Kartik, yeah.